Okay, let me try to get this set up here. The problems on solution 1 through 6, as far as it goes, 9, 10, 11, and there. Let's see how far that goes. Looks like it goes through number 10, really. 1 through 10. Some of the things you need to keep in mind, remember, given mass and volume, how do you get molarity? What you need to do is remember molarity is moles solute over volume solution expressed in liters. Moles solute would be mass in grams divided by formula weight. So that's a straightforward type problem. So, but it is critically important you don't get confused when the data comes at you and what they ask you, so you can apply the data correctly. Let's see. Solutions that are concentrates to diluted solutions, you could put down relationships, what we call the dilution equation. Molarity times volume of the concentrate equals molarity times volume of the diluted. But keep in mind, the idea of molarity times volume is the conversion for moles. Expressed in liters. And it comes out of the definition of molarity. Moles equals molarity times volume of solute in liters. I'm just going to scoot through this. Acid-base reactions are solution phase reactions. Let's say you have a reaction, it's like 7, 8, somewhere in there. Acid plus a base goes to a salt plus typically water or weak electrolyte in there. What are we looking at? When you write out the reaction, I'll use one, HCl plus NaOH goes to NaCl plus H2O. What are you looking at there? What can you calculate from that equation? Well, first, moles. There's 1 moles of high HCl. You have moles of the sodium hydroxide. You have moles of sodium chloride, and you actually have moles of the water. That's what it's saying. 1 to 1 to 1 to 1 to 1, based on the coefficients. That also means molarity times volume. So whatever you have in moles is equal to molarity times volume of the, say in this case, HCl, and equals molarity. Now we're talking about separate things. We're not putting equations together yet. Molarity times volume of the NaOH, and then you have also molarity times volume of the NaCl, and then you have molarity times volume of the H2O, because that's the definition of that. But you can also have, when you work these problems, let me see, I want to be sure we'll stay with the 1 to 1. Here is a 1 to 1 reaction ratio. What does it say about the number of moles needed? Well, whatever moles I have here is the same here. as well as here and here. That's a 1-to-1-to-1 reaction, right? So I can write, say if I'm given HCl and what do I do with NaOH? I can set molarity times volume, which is solution data of the HCl, equal to molarity times volume of the NaOH, because the equation says equal amount, equal moles, and moles is MV. You can also write that if the data comes to you. Say it comes to you in mass form. Moles of HCl equals solution form of NaOH, depending on how the data comes to you. You might have grams of HCl, say. You convert that to moles, but you got what volume of a 0.234 molar, and you'd have that. Then you can relate those two. Or you can have molarity times volume of the HCl acid equal to moles of base. So you see how those are all interrelated in there, depending on what kind of data you have. If you're given grams and you need, and part of the problem is in grams and part of it's in solution data, well, you need to set up something in this relationship. But it relates to the equation. Now, some of them will deal with salts over here. Say, how much salt based on data given in acids? Well, you have the same issue. Don't worry about water. It's either going to be acid, base, or salt on a problem. So you have molarity times volume of the acid equals molarity times volume of the salt. Or if the data, they want to know grams of salt generated, you might have solution data of the acid, molarity times volume of the acid equals moles of the salt. And if they want grams times the formula weight, that gives you grams. Or if you have, and you have, was there anything else on that? Yeah, moles of acid equals molarity times volume of the solution for the salt. So you see how that MV interrelates to the mole number, and it relates back here to the equation. This is a 1-to-1 reaction ratio. If I cut that in half mole and half mole, then they're going to be equal. Well, if this is in solution data, molarity times volume equals molarity times volume, well, something's missing in there. You solve for that. Everything else has been given. Okay. So, you want to keep in mind how the equations relate. Okay, let's say you have a solution phase problem. One of them was the H2SO4 plus 2 NaOH going to Na2SO4 plus a couple of H2Os out here. And the data that came to you was in terms of solution data. You have molarity and volume given on the H2SO4 and molarity times volume of the sodium hydroxide. So moles against 2 moles is the equations, what the equation's telling you. Which one's larger? Well, that's 2, okay? But that's equation data. Data. Now, to solve problems in this, what you need to do is take molarity times volume of, say, the H2SO4 and set it equal to molarity times volume of the NaOH. This is math data, math equations. From math, I know, just to categorize. But can you say these are equal for the reaction given? You can't say that the acid and the base are the same. But you can if you swap the coefficients. And then plug in your data and solve for the unknown. See the point I'm trying to make, guys? These are two different issues. You have to understand this one, this is greater than this. And the data is probably in molarity and volume. But in order for solve one against the other, you have to use molarity times volume equals molarity times volume. And the only way you can do that is say, well, if I double the acid over here, I will have it equal to this one. Isn't that true? If I multiplied whatever I have on that acid times 2, I'll get that. And then, or if I had H2SO4 like that, and if I want to set those equal, what would I have to do here? I'd have to cut that in half. What's half of 2? Okay? So that's why I say it's 1 there and 2 over here. Now you've got two things equal, and the data will fit that, but you have to swap the coefficients. Always start out picking the two reagents that are in the problem, one against the other. I got one in there that was kind of funky in terms of potassium chromate. You know, see which one that was. Yeah, number 8. You look at number 8 in your exam. It says the volumetric analysis of the experiment in an acid aqueous solution of methanol is titrated with a solution of potassium dichromate according to the following balanced equation. And that's an acid-looking equation, but it all boils down to just two reagents out of that reaction: the potassium dichromate and the methanol. So in that equation, you have 2 K2CrO4s and plus 3 CH3OHs and blah, blah, blah. Everything else is irrelevant. So once you find the two reagents in here that are central to that equation, set them equal. Molarity times volume of this potassium chromate and molarity times volume of the methanol. Now, in this form, you can't say those are equal. But if you take the coefficient on methanol, put it over here under the chromate, and the coefficient on the chromate, put it over here, now you can say that. Now throw in the data they got. Or you might have, let's see, in this one, they give you grams of methanol. Well, this side, instead of that, you'd have 2 moles of methanol. You'd work the mole-MV relationship that I showed you a minute ago. So you'd have 1.77 divided by whatever they gave you a formula weight, didn't they? They didn't give a formula weight in that? Well, whatever it is, formula weight. So you have moles over here equals 3 times, they have a 0.00389, 0.00389 molar. So the question is, how much volume? Now, if you have that, you ought to be able to solve for volume. That shouldn't be a big mystery, right? Hopefully, it's all of these kind of boil down to, in the reaction arena, the two reagents that you're working with. Write it down, molarity times volume, and set them equal, and then swap coefficients. No matter what the coefficients are, you swap them, you'll have an equality. And sub the data and solve for the unknown. On number 9, I had a number of questions come in on number 9 on the percentages. The context of that problem is to find the percent composition, how much of the whatever benzoic acid. Remember that the impure sample is a mixture, and when you're looking for percent composition, you're looking for how much of the pure sample in that mixture in terms of percentages. And it's always less than 1. Always. So times 100, and you have a percentage of that fragment. So percent, say for number 9, is part over total times 100%. And what did they give you? Well, the total mass is the mass of the mixture. That's the impure sample in this case. Let's see what they give you in here. An impure sample of benzoic acid is titrated with a 5.109 sample. So that would be 5.109 grams is the denominator in that. Now your problem, given the reaction and the data, is to get that part. That's the pure benzoic acid, H-benz, like that. So the reaction's given HBenZ plus sodium hydroxide goes to NaBenZ, benzoate, sodium benzoate, plus water. Well, it's balanced 1 to 1 to 1. So moles, and I ignore water. And that's the same as molarity times volume of the H-benz, molarity times volume of the NaOH, and if you use the salt, I don't think that's in there. So what does it say? It says a 5.109 gram requires 36.97 of the titrant, which is 0.8067 molar. So the titrant is 0.8067 molar, and you used what? 36.97 milliliters. Okay, what's the percent mass? Well, this is in moles. I need to get this over here in grams. Well, you have to go to moles first and then times the formula weight, and it gives you that 122.12. So we need to set it over here moles, because moles can go to grams of the pure stuff, which you'll put in the numerator, if you understand what I'm telling you. And that's all you're doing. Moles equal moles. So what am I saying? So start out with molarity, volume, but if you are given, if you need grams, then one side is going to have to be moles, not MV, but the other side is MV. Now, if that's the case, unless both sides are the same dimensions, you can leave it in milliliters, but you can't use that if one side's just in moles. That has to be in liters. So it's 0.8067 molar, and you recall that's moles over liters, times 0.03697, liters. And so whatever that comes out is the moles of benzoic acid, because it's a 1 to 1. Because you calculated the moles of sodium hydroxide used, it's also 1 to 1. So if you've got the moles of sodium hydroxide, you also have the benzoic acid. And whatever you get out of this times 122.12 grams per mole gives you the grams of H-benz. And whatever that comes out, you put in the numerator up here, part over total. Please study that. Go down here. Number 11 is a math. It's just an algebra manipulation problem. For certain, let's see. Okay, number 11 confused some people. For a certain first order reaction with the general form A goes to products, the rate of that reaction is 0.32 molar dot seconds to the minus 1. Well, what does that mean? That is 0.32 molar per second. Look at it like that. When the concentration of the reactant is 0.29 molar, okay, so A equals 0.29 molar. What is the rate constant for this reaction? Well, what's your rate law? Is rate is equal to K onto A raised to whatever is a first order reaction, I think it says. Yeah. So X is already 1, like that. So what do? You solve for K, rate over concentration. Rate was given 0.32 molar per second, and A was given 0.29 molar. Molars drop out, and so whatever that comes out to be is in seconds to the minus 1. All of your K values are going to come out in reciprocal seconds in these first order type reactions. Number 13, if a reaction is first order with respect to a particular reactant, when the concentration of the reactant is increased by a factor of 2, the reaction rate will do what? Now, this has to do with orders of reaction. Let me see which one, 13. And rate changes. Now, this is order of reaction relative to concentration changes. If you double concentration and you double rate, that's a first order. If you double concentration, you jump 4 times, that's second order. If you double concentration, nothing happens, that's 0 order. Okay? So you need to know those. First order. Okay, A goes to 2A, and rate doubles. First order. In second order, A to 2A, rate increases 4 times. If you change concentration, you don't get any change, it's 0. Let's see. Yeah, 14. Very important note here, more of a factoid than anything else. In yesterday's lab work, I had, let's see, 14. What we did, the raw data was kind of like this. This was pH, which is essentially concentration of whatever's going on, against time. And what you observed, and you can look on your sheet right there, and right here is what we refer to as the initial rate of reaction. At time 0, right after the horses jump out of the gate, is the fastest point of a reaction. Right after you open the gates. Anything else is slowing down as it goes forward in there. Instantaneous rates, they're slowing down. Okay, so in number 14, it's asking the rate law for the reaction between this is K on 2 NO2 and Cl2. Okay, which of the following changes will not alter the initial rate? Will not move this up or down? What will not move that up and down? Increasing the concentration of NOCl. Well, you have, let me write the reaction out. 2NO plus Cl2 and 2NOCl. Make sure I'm, okay. A, increasing the concentration of NOCl. That's not going to affect anything. I think the answer to this one's A, I think. The rate law is in terms of reactants. So the rate of reaction is dependent on only on the reactant. It doesn't, you're going to make products over here. It doesn't matter how many products you make, they came from the reactant side. And so increasing this one over here doesn't mean anything. Let's see what else. Decreasing the volume of the reaction system. Yeah, you decrease the volume, you increase pressure. Okay, and so that's definitely going to force the reaction to go faster toward the product side. Running the reaction as solvent rather than a gas phase. Yeah, you'll have a change, and you'll change the rate, because in gas phase it has one K value, and in the solvent it's going to have a different K value. Increasing the volume of the reaction system, that's just opposite of decreasing. Increasing the concentration of chlorine gas. You're damn right it'll shift the reaction. That's the increased concentration, increased rate of reaction. So the only one in there is not going to do anything is, how do you increase the product if it ain't been formed yet? Open the gauge, yeah, okay. Yeah, it'll start running. So there's some intuitive questions in here where you have to know that what affects the rate of reaction, CANTC, as applied to reactants. Not product, because the rate law is all in terms of the reactant. Because when we draw that time concentration curve, I'm showing reactants and you're showing a decrease in, increasing in products that are generated, but the reactants define the reaction going to those products. Okay. Oh yeah. Here's one. In some problems, you're going to be in the decay problems. A equals A sub O e to the minus KT, just some notations here. Remember also KT to the 1/2 equals 0.08206, and T equals ln of A over A sub O over minus K. This one is the standard form of the first order decay equation. A here is the final concentration. That means how much remains. Not how much has been consumed. This equation, time factor, is based on a half-life. This one is time of decay. Different from the half-life time. So, now, one type of problem is you will have to use they give you a half-life and ask you something where you have to use the decay equation. You'll have to use the half-life equation to get K and then solve for T using this second one. So check mark that you may have to use the half-life equation to get K and then solve for T. I'm giving you that go T, and that time is not a half-life. That's a general time of decay. All radioactive decay is first order kinetics. Let's see, I made a bunch of notes here. I still got a few minutes. I want y'all all make an A on my exam. Okay. Number 17, I made a note of 17, wasn't it? Not in 17, wait a minute. Oh, use this half-life equation. Oh, 18. What would happen if the kinetic energy of the reactants were not enough to provide needed activation energy? Nothing. You look at number 18. You recall the Boltzmann curve like this, and then I drew a line over here. If this line represents what we call the delta EA, activation energy point, right there. Okay? And so any reactants over here, there's no reaction will occur if reactants have energies in here. They have to be at or above that activation point in order to achieve products. And at that point, you have the CENT factor. If kinetic concentration, effective collisions, reactive components, and enough energy due to temperature to be at or above the activation energy. Okay, then you'll have to know your difference between your potential energy diagrams for endothermic and exothermic. And then enter the data, but split in either or type problem, split it in the middle, and you have values. This is your activation point right here, and this is the delta EA reversed for this one. It's delta EA forward here, and this is your delta E of reaction here to here. Some of those two get the big side. But on the endo, it's opposite that. You see, this is your delta E of your reaction. This is delta E reverse, and this is delta E forward. So reverse plus heat of reaction gives you your forward side. Split it in half and then apply the data given. Solve for the unknown. Okay, do know the Arrhenius equation. Over R. That's that's the activation energy. T2 minus T1 over T1 times T2. Now you'll have a problem on solving for activation energy, and you'll have a problem where you'll have to determine the rate constant. This means Ln of K2 minus Ln of K1 equals all the other stuff on the right side. Okay, number 21. I think you have to use the ICE table. It gives you setup on that one. Use the ICE table, initial change, concentrations. And let's see if I can Okay, from 22, well, from 21 to the end of this practice exam is all equilibrium. So that's kind of what we covered today. Let's look at number 21 in here. The Oswald process converts ammonia to nitric oxide by reaction with oxygen in the presence of a catalyst at high temperatures. A test of the process, let's see, we've got 4NH3 plus oxygen goes to 4NO plus 6H2O. In a test of the process, a reaction vessel contained 3.9 moles of ammonia, 4.9 of oxygen, and heated to a high temperature. When the equilibrium was established, it was found that it contained 2.9 moles of the nitrous oxide. So this is initial change in equilibrium. And so these are zeros because the reaction hadn't started yet. Where'd it go to? 2.9. But this one is down here. Now you need to be able to set up that ice table and enter the appropriate data where it should be. Typically they give you the reactants and then you put in zeros for the products and then come down and build the equilibrium rod. Then you make in the, of course the reactions shifting left to right, so these are going to go down in concentration and products are going to go up in concentration. So that means minus 4x, minus 5x, this one's plus 4x, that one's plus 6x, like that. And then to get the rest of them, that's 3.9 minus 4x, 4.9 minus 5x, and then 0 plus, and it's 6x right there. Well, you use this one to get the x, and then plug them into equilibrium rod. That's easy as pie. You ought to be able to handle that. Also, all right, here's one where they give you the equilibrium. In number 22, the problem starts /data is at equilibrium. You don't have to use the ice table. They say at equilibrium, they have found the concentration to be blah, blah, blah. So all you have to do is write the Kc expression, products over reactants, and plug in the data. So be careful how you read the problems. Which of the following reactions are, for which of the following reactions are the numerical values Kp and Kc the same? Kp equals Kc if and only if the sum of the change in molar volumes of the reactants equals sum of the change in molar volumes of the products. Let's see which one. 2, 3, 2, no. Number 2 is, and 3 is, N2 gas plus O2 gas gives you 2NO gas. Well, here you have 2 molar volumes and 2 molar volumes. Delta molar volumes is 0, which is 2 minus 2 makes N, or delta N in the KPKC expression, equal to 0. And I show you Kp equals Kc RT to the plus delta N. Well, if that's a 0 right there, this term goes to 1 and Kp equals Kc. That's why I say it's only condition. But if these are different, like in equation 1, you have a compression there, 3 on the left, 2 on the right. That's, you can't say Kp equals Kc there. But in 2 and 3, looks like the molar volumes on the left equal molar volumes on the right. So D choice in that one. Okay. 24. The value of Kc for the reaction here is that, what's the Kc for the given reaction? This is one of those manipulation type problems where you have H2 plus Br2 gives you 2HBr and K equals 2 10 to the 19th. What's the Kc for? Looks like they reversed it and cut it in half. So they have HBr goes to half H2 plus half Br2, and K2, like that one, is the question. So what you have to do is you have to compare K expressions and see how you got there. So for number 1, K1 is HBr squared over H2 times Br2, and K2 is equal to H2 to the half Br2 to the half over HBr. So how did you get there? Took the reciprocal and square root. So K2 is 1 over the square root of K1. And you plug that in and I gave you a number. Okay, this is where you multiply the two K values together to get your net reaction number 25. K1 times K2. Kc is just writing the equilibrium expression. 27 is, which of the following values of equilibrium consistency reaction mixture contain mostly reactants? It's the one that has the smallest value, 10 to the minus 9. Okay, here's shifting 28, 29. They give you a reaction here. What is that? C2H6 plus C5H12. Your smithing plus C6H14 plus, that's it. Okay, and the Kp for this reaction is 9.57 times 10, 9.5, I thought it was a power. 9.57 at whatever temperature they give you. What can you conclude about Kp, Kc here? Are they equal? Two molar volumes, 2 molar volumes. Look back, remember what I said? If the molar volumes is reactants, if the molar volumes is products, Kp equals Kc. So this is also equal to Kc. Now you take the data that's given, suppose 47.2 grams of each of those are placed in a 25-liter vessel. Well, if you take 47.2 grams of everybody, right? What it's saying, convert those to moles, formula weight of C, whatever that one is, formula weight of that one, formula weight of that one, and that'll give you moles of each one of those. Then you divide those by the volume. What's the volume of this 25-liter vessel? Okay, once you get them in molarities, That would give you the moles per liter that you're mixing together. Then you can get the QC value, which is CH4, C6H14 over C2H6, C5H12. And you plug in your data into that, and you get your KC value. When you get that number, you go KC equals 9.57, and QC equals whatever that one is. And if you keep K first and Q second, the inequality, if there is one, will answer that question real fast. Hopefully you study that. Same way with 29, it's left-right shift. Uh, 30, look at 30 as a partial pressure problem, and you set it up just like you'd set up a concentration problem. But one of the components in the equilibrium expression is left out, so that's the one you're trying to solve for. So if you're given N2O4 and 2NO2, the KP expression is the partial pressure of NO2 squared over the partial pressure of N2O4 to the first power. And all of that is 0.15 given, so that's given. And what else is given in here? It is found that partial pressure of N2O4 is equal to 3.2 times 10 to the minus 2 atmospheres. That's to the first power in O2 squared. So solve for the unknown. So check that out. Okay, they got in an experiment 40.42 mole of H2, 42 mole of I2 are mixed in a container. The reaction forms HI. Kc equals 49. What's the equilibrium concentration of HI? I think you in 1 liter, so that's the molarity is also. So for 31, which way are we going here? I2 plus H2 is 2HI, and so you have 0.42 molar, because divided by 1 mole, 1 liter. And then you have a 2x at the equilibrium. Well, if you set up Kc is HI squared over I2 and H2, and that's equal to 49 to equal H2x squared, and then 0.42 times 0.42. And then you solve for x. Take the square root of both sides. Okay? Or like that, and that'll give you x, and plug it in, and you got the answer. Which of the following would be affected by volume changes? See, that's what I was telling you. Now, this type of problem is asking about volume changes, but you have to interpret it in terms of pressure changes, and then determine which way it'll shift. like B choices. Well, it's not equal on the molar gas size. Oh, this is just, yeah. It would shift to the low side. If you increase pressure or decrease, it shift to the high side. There, 34 is a thermodynamics type problem. And so you're looking at an endothermic reaction given. So what you have to do is place kind of a hypothetical into the reaction and then read the changes. There's your delta H of reaction on endo. Okay, what does it say? High temperature or low pressure. For an endothermic reaction given, the conditions that favor maximum conversion. So we want to find the conditions that will shift that to the right. With high temperature and low pressure, we got 1, 2, 3 molar volumes and 4 VM, and you got an energy number there. So increasing temperature, but increasing pressure shifted to the left. High temperature, pressure being unimportant, always important. Low temperature, shifted to the left. Low temperature, high temperature, high pressure. High pressure, 3 to 4, yeah. High temp, high pressure, shifts it to the right. So you have to make these kind of decisions based on what I taught you today on pressures. Oh yeah, and something like 35, 36, 37, those kind of things. There's some more solution problems. Remember, if you have solid stock, in other words, manufactured solid, is grams equal molarity times volume times formula weight over your purity factor. If you have manufactured liquid, is milliliters equals molarity times volume times formula weight over your purity factor, and you have to include specific gravity, which is density number. If you have to dilute, the dilution equation, molarity times volume of the concentrate, molarity times volume of the diluted sample. With a kinetic one. Nitrosyl chloride. The following initial rates are given at a given temperature were obtained from the concentrations listed below. From the data, what is the rate law? You have to look at the data and see what you change concentration, you change rate, you have to define first order, second order, zero order, or whatever, and come up with the equation. 36, 37, 38, 39, solution problems, dilution problems. 42. The only thing that will affect the activation energy is a catalyst. Catalysts function by connecting to something in the reactant side and bringing the reactants together to achieve products. At the intermediate stage, they fall off and are not consumed by the reaction, but they make the products. And in doing so, say here is a potential energy curve. This is your delta E point, delta EA normal. Well, if you add a catalyst in there that speeds up the reaction, it'll drop that down. So that is a new activation energy, lower hill, faster reaction. That's how catalysts work. Or if you put something in that raises that activation energy, that's a higher hill, slower reaction. I see I'm out of time. But concentration effects just tilt the reaction and shift it. Temperature effects, all they do is raise the If you heated it, it raises this, but this doesn't change. You bring yourself closer to the activation energy, but it doesn't change the activation energy position. It just goes faster because you don't have as much of a hill decline. Well, guys, I'm out of time. I will have it ready for you at 10:15 in the morning. See y'all tomorrow. Study, study, study. Could you put that brick down there for me? Thank you. Y'all have a good day. Whew. And I'll be close to the computer all night. If anybody has any questions. Now I gotta go to work. Yes, ma'am. Oh, you're welcome.
Yeah. Are the questions that like
Yes, dear.
are the questions that like don't have numbers? Are those going to be the same?
Let me get real close.
Are the questions that like aren't like numerical? Are those going to be the same questions?
Well, they won't have the same numbers.
The ones that don't like
And some of those
like the
may
more
not be on
conceptual
there.
questions.
Huh?
Like the more conceptual questions, will those be the same as well?
Conceptual questions?
Yeah.
Like which ones would not affect the activation energy?
Yeah. Are they going to be the same on the test?
I can't say that.
Okay. So
I
there's
can say that the ones that are numerical may be,
Okay.
but they are, I changed the numbers.
okay. Thank you.
Okay? And yes and no.
Okay.
Okay. Yes, ma'am, by all means. Have my undivided attention.
On 42.
Oh, yeah, that's the only one. See, increasing or decreasing reaction temperature only brings the potential internal energy of the reactants closer to the activation energy. But an activation energy for a given reaction is characteristic of a reaction. The only way to change its activation energy is to put a catalyst in. And it attaches to the reactants and proceeds to achieve the reaction factors faster. That's how that works. But all this does is it raises the, hang on, baby. I'll give you.
No, I was just throwing it in there.
Okay. All this does is it raises the potential energy of the reactants closer to the activation point. It just raises it up. Okay? Increasing, decreasing the concentrations. It increases the rate of reaction because the kinetic concentration is higher. But it doesn't change the activation energy point. It just increases the number of products. That's why first order increases because of more collisions and that kind of thing. Is that your question?
Yes, I misinterpreted what it was asking, and that makes sense.
Yeah. Only thing in that collection of CENT, can't see, is C. That's the only one that'll affect the activation energy. Okay? And you can explain that also using the Arrhenius equation. Delta K equals A onto E to the delta E over RT. If you know what I'm talking about.
Mm-hmm.
Okay. Yes, sir.
Can I access the lab folder from any computer, or do I need to be in the lab?
I don't think so. You have to be on the. Wait a minute. Let me think. Can I do that? I could test it and find
Oh,
out.
you could, yeah. I didn't even think about that.
Yeah. Let me.
Yeah, because
I'll let
we
you have a
can
good
email
day,
each
dear.
other
Have a good day. I just.
the information.
Okay.
So I was hoping
Let me
we could do
stop.
that.